Good day, everyone. Today, we are going to explore the world that is extremely small, but its impact on our life is very big, the nano world. But before we proceed, this will be our lesson objectives. By the end of this lesson, you should be able to define nanotechnology, identify the characteristic of nanoscale, discuss the impact of nanotechnology on society, examine the costs and benefits, and explain social and ethical consideration. Nanotechnology is the science and technology of working with materials that are extremely small. In simple words, nanotechnology is all about creating, studying, and using very small materials to improve products, medicines, and machines. And also, nanotechnology is already being used in many things that you use every day, such as cell phones, medicines, computers, sunscreens, and clothes. And now, let's proceed to nanoscience and nanotechnology. Nanoscience is the study of things at the nanoscale. It is all about learning and understanding how tiny particles behave. And nanotechnology, this is the application of what scientists learn from nanoscience. It focuses on using this knowledge to improve materials, build new devices, and solve real-life problems. So, in short, nanoscience is the knowledge, while nanotechnology is the application of that knowledge. And now, let's proceed to the concept of nanoscience and nanotechnology. The idea of nanotechnology was first introduced on this date, December 29, 1959, by Richard Feynman. Richard Feynman is also known from the phrase, "There's a plenty of room at the bottom," meaning there's still a huge opportunity to explore and build things at very small scales. And also, it is coined by Professor Nario Taniguchi, who was the one who officially introduced the term nanotechnology.
So let's talk about how small is nanoscale, one of the most important ideas in nanotechnology. What is nanoscale? It is a branch of nanotechnology that deals with very tiny structures. Tools used in this field measures in nanometers. 1 nanometers equal 1 billion of a meter. Imagine dividing a 1 meter into a billion pieces. That tiny pieces is 1 nanometer. The picture shows different objects from very small to big, like DNA about 2 nanometer, bacteria about 2000 nanometer, water droplet millions of nanometers, human hair strand about 80,000 nanometer thick, house many meters, so billions of nanometers. Nanoparticles or viruses fall into the nanoscale range 1 to 100 nanometers. For example, in human hair is like the width of a big track tree, then a nanoparticle is like the width of one leaf vein, super tiny and invisible to the naked eye. Since nanoscale objects are extremely tiny, regular microscope cannot see them, so scientists use special microscopes, like electronic microscopes. It is invented in the 1930s by Ernest Ruska and Max Knoll. Uses a beam of electrons, not light, to view specimens. Produces higher resolutions than old light microscopes, meaning much clearer and more detailed images. So, there are two types of electron microscopes. First is transmission electron microscope. Sends electrons through the sample to see inside structures. Second is scanning electron microscope. Scans the surface to create a 3D like image. For example, in scanning electron microscope, looking at the textures of an ant's body. In transmission electron microscope, seeing the internal structures of a virus. Other tools to view nanomaterials is atomic force microscope, invented in 1986 by Gerd Binig, Calvin Coate, and Christoph Gerber uses a tiny mechanical probe like a very sharp needle. The probe touches the surface of a material to gather details. For example, in atomic force microscope can feel tiny bumps on a surface like reading braille but on atoms and molecules. Scanning tunneling microscope. It is invented in 1986 by Gerd Binig and Henry Schur. They won the Nobel Prize in the physics for this invention. Allows scientists to view and manipulate atoms and nanoscale particles. Uses quantum tunneling to detect the surface of materials. Using scanning tunneling microscope, scientists can position atoms one by one, like arranging tiny Lego blocks made of atoms.
So let's proceed to nanomanufacturing. Nanomanufacturing refers to producing materials, devices, or system at the nanoscale, meaning incredibly tiny structures measured in nanometers. When we say scaled up, reliable, and cost effective, it means scaled up. The process can be done not just in the lab but also in large quantities for industry. Reliable, the results are consistent and high quality every time. Cost effective, the methods are not too expensive, making production practical. In short, nanomanufacturing is the large-scale production of extremely small materials and devices, ensuring they are high quality and affordable. So now let's talk about the two fundamental approaches to manufacturing. So first is bottom-up fabrication. This approach builds materials starting from the smallest units, atoms or molecules. Think of it like building a house brick by brick. Atoms or self-assembly join together to form the desired structure. Example, chemical vapor deposition. Atoms arrange themselves on a surface to build a layer. The second one is the top-down fabrication. This does the opposite. It starts with a larger material and then trims it down to nanoscale size. Think of it like sculpting. You carve or cut a big block to get a tiny product. For example, etching or milling to create very small circuits in electronics. So now let's proceed to new approaches to the assembly of nanomaterials. The first one is deep bend lithography. Uses the tip of an atomic force microscope or AFM like a pen. The tip is dipped into a chemical fluid. It writes patterns on a surface, like an old-fashioned ink pen on paper. This allows drawing extremely small features. Its purpose is to create nanoscale patterns for electronics, sensors, and materials. The second one is self-assembly. This approach lets materials organize themselves without outside guidance. Components naturally arrange into structure because of chemical or physical forces. For example, molecules automatically forming into patterns or layers. In simple words, the structure builds itself based on how the molecules attract or repel each other. The next one is chemical vapor deposition or CVD. Chemicals in gas form react on a surface to create very pure, high-quality thin films, often used in making semiconductors, solar panels, and nanomaterials. Think of it as gas turning into a solid layer on a surface through chemical reaction. The next one is the nano imprint lithography. A mold or stamp is pressed onto a surface to transfer nanoscale patterns, similar to stamping design onto clay, except at a nanoscale. Its use is to creating a precise patterns used in electronics and optical devices. The next one is molecular beam epitaxy, or MBE. It is a very cold controlled method of depositing extremely thin layers of atoms on a surface. Atom beams are directed towards a heated surface where they form a film. Its advantage is it's one of the most precise ways to make high-quality nanostructures. It is used in semiconductors, quantum devices, and high-tech electronics.
Now we are down to new approaches to the assembly of nanomaterials. So say roll-to-roll processing. This is high-volume manufacturing technique used to create nanoscale devices in a continuous roll of ultra-thin plastic or metal. And the second is atomic layer epitaxy. When I say atomic layer epitaxy, this is a method for depositing one atom thick layers on a surface. Now we are down to the distinct features of nanoscales. Nanotechnology operates a very small dimension, allowing scientists to utilize the exceptional optical, chemical, physical, mechanical, and biological qualities of materials at small scales. Now we are on a scale at which much biology occurs. So we have biobarcode assay. It has polydotylab monoclonal antibody, gold nanoparticles, probe, magnetic probe, target protein, target capture, sandwich with AUNP, barcode tags, magnetic capture and barcode dehydratization, PCR for on-chip detection. So those are the things that was shown in the image here in our slides.
In this slide, we will talk about how materials behave differently when they become extremely small at the nanoscale. At the size of quantum effects, it will start to dominate. So this means their color, behavior, and properties change even if the materials itself stays the same. Here we can see at the pictures the nanoscale gold in two forms. First is the nanorods and second is the nanoshells. For the nanorods, the only thing changes is the aspect ratio, or how long or wide the rods are. But as you can see, these simple changes causes the gold solutions to show different colors from blue to green to red. And also for the nanoshells, it's the shell thickness. Ang ila ang kabag-on is maoray mausob. So again, even though they are made of gold, different thickness produced in different colors. So this shows that at the nanoscale, gold behaves differently because of quantum effects. Next is we have another important property of nanomaterials. So when materials are broken down into extremely tiny pieces, their surface area become much larger even if the total mass stays the same. So this large surface area makes nanomaterials more reactive, more efficient, and more useful in a wide range of applications. This is why nanotechnology is widely used today in medicine, electronics, cosmetics, and environmental technologies. So we will always simply put that the smaller the particle, the larger the surface area, and the more active the material becomes. Lastly, let's look at the government support for nanotechnology. The United States has one of the biggest programs in the world called the U.S. Nation's Nanotechnology Initiative, or NNI. This program was established in 2001 to coordinate federal research and development in nanotechnology. And as shown in the slide, the U.S. invests a very large budget in this field, around $1.4 billion in 2008 and $1 billion in 2009. This shows how important nanotechnology for future development in health, defense, materials, and science, and many other industries. Governments invest heavily because nanotechnology has a huge potential to shape the future. So this slide shows that nanotechnology is a powerful field. At at the nanoscale, material gain new properties, become more reactive and more useful. And because of its importance, countries all over the world invest huge amounts in nano research technology.
European Commissions. Europe wanted to compete with the USA and Japan, so it creates the European Nanoelectronics Initiative Advisory Council o ENIAC in 2008. ENIAC helps European Union countries to collaborate instead of working separately. It supports research in nanoelectronics, materials development, and large-scale industrial application. This initiative strengthens the EU's global standing in microchips and sensors. Japan Nanotechnology Research Institutions. Japan is known for its strong electronic and materials industries, so it's heavily invests in nanotechnology. Nanotechnology Research Institution under AIST supports advanced research in nanoelectronics, new materials, robotics, and biotechnology. Japan focuses on creating high-quality industrial applications such as semiconductors, optical devices, and medical technology. Taiwan National Science and Technology Program for Nanoscience and Nanotechnology. Taiwan's programs support nanotechnology for semiconductors, electronics, and manufacturing, which are central to Taiwan's economy. It creates a partnership between university and big technology companies. Helps Taiwan maintain leadership in microchips and electronic productions. India Nanotechnology Research and Education Foundation. India invests in nanotechnology to expand in scientific capacity, support trainings, education, and development of research capacity. Focuses on medicines, agriculture, and material science. The goal is to catch up the more technologically advanced nation. China National Center for Nanoscience and Technologies. China has rapidly become a global leadership in nanotechnology. And CNST integrates government supports with strong university and industry partnership. Focus areas including new materials, energy, electronics, biotechnology, and large-scale commercial application. China aims to be at the forefront of future nano-based industries. Israel National Nanotechnology Initiative. Israel has a strong research culture and invests heavily in high-tech fields. This initiative funds university encourage development of nano-based startups, primary areas nanoelectronics materials, and defense application. 8 is Australia. Australian Office of Nanotechnology. This office coordinates national policy, safety guidelines, and research funding. Focuses on medicines, environmental technology, and materials engineering. Ensures safety development of nanotechnology throughout the country. Canada National Institution of Nanotechnology o NINT supports advanced research developments in material science and biomedical application. Canada integrates university research in industry needs, strong in materials, energy, systems, and health technologies. 10 is South Korea National Technologies Initiative. South Korea uses nanotechnology to strengthen in the electronics and manufacturing industries. Very competitive in semiconductors. Government funding supports and nanoelectronic materials, robotics, and energy technologies. Thailand National nanotechnology centers. Thailand centers focus on research that direct addresses national needs like agriculture, health, food safety, environmental protections that helps build human resources and local expertise in nanotech. Malaysia National Nanotechnology Initiatives o NNI. Malaysia invests in nanotechnology to improve industrial competitiveness. Programs aim to integrate nano-based products into manufacturing and agriculture. Also support training and education to build national expertise. Possible of nanotechnology in the Philippines according to Diary 2005. Diary identifies sectors where nanotechnology can make a significant difference for the Philippines. First is ICT and semiconductors. The Philippines is already active in electronics assembly. Nanotechnology can improve microchip performance, create smaller and faster electronic components, support sensor development. This helps strengthen the country's ICT industry and competitiveness. Second is health and medicines. Nanotechnology can improve healthcare through target drug delivery, early disease detections, more effective diagnostic, and medical imaging. So this could make healthcare more efficient and accessible in the Philippines. Third is energy. Nanotech can help develop better solar panel, more efficient batteries, and fuel cells. This can support renewable energy efforts and reduce dependence on imported fuel. Fourth is food and agriculture. Nanotechnology can enhance agriculture productivity by building slowly releasing fertilizer for effective pesticides, nanosensors for soil and crop monitoring, improves food packaging and preservation. This help can address food security and agricultural change. 5 is environment. Nanotechnology offers solutions for environmental problems. Nanomaterials for water purification, sensor for detecting pollutants, materials that break down contaminants, and this can help the Philippines address issues like water pollution and waste management. In summary, countries around the world invest in nanotechnology because it has massive potential to reshape key industries. According to the 2005, emphasized that the Philippines should adopt nanotechnology to benefit sectors such as electronics, healthcare, agriculture, energy, and environment. These areas can derive national development, economic growth, and innovation if the country invests early.
Nanotech Roadmap for the Philippines. Study number 1. ICT and Semiconductors. The researchers are Dr. Arnel Salvador, Dr. Roland Samago, Mr. Amando Somintak, and Michael Defensor, the research assistant. So this study focuses on how nanotechnology can improve information and communication technology or the ICT and semiconductors devices. Nanotech can help create faster, smaller, and more energy-efficient electronics such as improved microchips and processors, high-performance sensors, better data storage technology, and stronger and more efficient electronic materials. So, the goal of this research is modernize the Philippines electronics industry so it can compete globally and support advanced tech manufacturing. Study number 2. The Health and Biomedical. The researchers of this study is Dr. Carlo Marblanca, Dr. Bessie Basilia, Dr. Cynthia Saloma, and Dindi Samsuya. So this study explores nanotechnology applications in medicine, healthcare, and diagnostics. So nanotech can revolutionize medical practice through nanodrug delivery that precise targeting of medicine within the body. Early disease detection using nanosensors, bioimaging tools for cancer and other critical diseases, antimicrobial nanomaterials used in hospitals, and development of biomedical devices. So the goal of this study is to improve the country medical technologies, promote earlier detections of diseases, and create more effective treatments. Study number 3. The energy. The researchers of the study is Dr. Jim Minglana, Dr. Erwin Enriquez, Dr. Jerry Nuesca, and Ian Harvey Arellano. This study investigates how nanotechnology can improve energy reduction, storage, and efficiency. Nanotech solutions include better solar cells that convert more sunlight into electricity, improved batteries and supercapacitors that longer lasting and faster charging, fuel cells and alternative energy system, and nanomaterials that reduce energy waste. So the goal of this study is to support the Philippines shift to renewable energy and create reliable, eco-friendly power system. Study number 4. The environment. The researchers of this study is Dr. Fabian Daywright, Dr. Christina Binag, Christian Manapit. So this study explores new nanotechnology can help protect the environment and solve problem solutions. So possible applications is the nanomaterials for water purification, nanofilters that remove heavy materials of toxins, air purifying nano coatings, environmental sensors that detect pollution faster, and the nanotech solutions of waste treatment. So the goal of this study is to use nanotechnology to address Philippine environmental challenges such as water pollution, waste management, and air quality. Fifth study is the agricultural and food. The researchers of this study is Dr. Milagros Peralta, Dr. Fortune Sevilla, Dr. Antonio Laurenia, Dr. Veronica Sabolarse, and Ruby Ortiz, the research assistant. So this study focuses on how nanotechnology can improve agricultural, food security, and food safety. Examples of applications are nanofertilizers and nanopesticides for healthier and more efficient crop growth, soil and plant sensors for smart farming, improved food packaging that keeps food fresh longer, detection of food contamination using nanosensors, and nanomaterials that enhances crops resilience. So the goal of the study is to increase agricultural productivity and ensure safer, higher quality food supply.
So let's proceed to study 6, which is the health and environmental risk. The researcher is Dr. Florida Carino. She studies how nanotechnology can affect human health and the environment, including possible dangers. Study 7, which is the nanometrology. The researcher is Dr. Erwin Enriquez. Nanometrology means measuring tiny particles accurately. He works on tools and standards to measure nanomaterials correctly. Study 8, which is the education and public awareness. The researcher is Dr. Fabian Dairit. He helps improve public knowledge and awareness of nanotechnology, ensuring that teachers, students, and citizens understand it. And now, let's talk about the benefits and concerns of the application of nanotechnology in different areas. These are examples of areas affected by nanotechnology. So first, we have environment. So this is the possible benefits. Better detection and removal of contaminants. So nanotech can help identify and clean up pollutants in air and water faster and more effectively. Greener industrial processes. Companies can use nanotechnology to create materials and products that are safer for the environment. And here are the concerns. High reactivity and toxicity. Because nanoparticles are very tiny. They may react strongly with other substances and could be toxic. Wide environmental spread. Nanoparticles can easily spread through air, soil, or water because they are so small. Lack of regulation. There are no nanospecific environmental regulation, for example, from the EPA, so safety rules are still unclear. Next is health. Possible benefits. Improved medicine. Nanotech can create better drug delivery systems, more effective treatments, and early disease detection. So here are the concerns. Ability to enter cells. Nanoparticles can pass through cell membranes and move inside the body, which can be dangerous if toxic. Limited regulation. For example, cosmetics and supplements with nanotech may not need FDA approval, which raises safety questions. And last, economy. Possible benefits. Better products. Nanotechnology can improve electronics, clothing, cosmetics, food packaging, and etc. New jobs and industries. The demand for nanotech experts increases job opportunities. Accessibility. Nanotech products could eventually become affordable for everyone. And here are the concerns. Cleanup and healthcare costs. If nanomaterials cause pollution or health issues, they could be expensive to manage and treat. That's all.